It is true almost all the time that things do not stay static. Things will tend to be put under stress and be knocked out of balance, but nature always favors balance, so it will always go back to this balance to get back on track. In a chemistry point of view, this is what the video will be about: restoring the balance. So today, we will be talking about what happens when you disturb a reaction in equilibrium. Don't worry, there won't be any complicated math in this video. Before we begin, let's have a short recap of what you should know so far. In the concept of equilibrium, reversible reactions with its initial concentrations will go towards equilibrium where the forward and reverse rates of reactions are equal. The concentrations present in equilibrium for a reaction of this form can be expressed to define an equilibrium constant specific for the reaction. This equilibrium constant is known as Keq or Kc and is mathematically expressed in this equation, even though we are not limited to just 4 reactants. The bracket enclosing the reactant just means the concentration of the enclosed reactant. So basically, the equilibrium constant is the product of the equilibrium concentrations of the products, each raised to the power of their respective coefficients, all divided by the product of the equilibrium concentrations of the reactant, also raised to the power of their respective coefficients in the balance equation. Yes, never forget to balance your chemical equations first. Aside from our equilibrium constant, we also have a quantity called the reaction quotient with a variable of Q. This quantity predicts the direction of the reaction and will prove to be super useful in analyzing disturbances in a system in equilibrium, as we shall see later. Here are 3 simple rules to show how you can predict the direction of the reversible reaction. If Q is less than Kc, the reaction proceeds to the right, meaning it favors the products. If Q is equal to Kc, the reaction is in equilibrium. If Q is greater than Kc, the reaction proceeds to the left, meaning it favors the reactants. Q here is defined very similarly to Kc, but the concentrations aren't necessarily at equilibrium.
Now, when a system is at equilibrium, it stays at equilibrium unless disturbed. What do I mean by disturbed here? By disturbed, I mean conditions affecting the equilibrium of that system is changed. How? There are 3 ways. 1. By changing the concentration of the reactants or products, though I only really mean those on the left and the right sides of the equation. 2. By changing the pressure or the volume for the reactions that involve gases. Or 3. By changing the temperature. After you've applied these stresses, the reaction will shift in the direction that will reduce the stress, as said by Le Chatelier. In other words, if you disturb it, it'll find a way to get itself back to equilibrium. As you can probably tell, Q will be playing a big role here. Let's talk about changing concentrations first. Looking back at the definition of the equilibrium constant, adding or subtracting the concentration of each of the substances will of course change, such that Q will no longer equal Kc. Then, you can compare Q to Kc to find out how the reaction will restore itself to equilibrium. Analyzing from a mathematical perspective, if you increase the concentrations of the products or decrease those of the reactants, again, no real products or reactants in a reversible reaction, the value of Q will be larger than Kc. Hence, the reaction proceeds to the left. Likewise, if you decrease the concentrations of the products or increase the concentrations of the reactants, Q will be smaller than Kc, which indicates that the reaction will proceed to the right. This may seem a bit confusing at first, but this basically means that if there is a lack or excess of a substance in the reactant or product side, the reaction will proceed in the direction that either makes up for this lack or gets rid of the excess in order to bring itself back to equilibrium. More often than not, it would be somehow hard to apply this logic when all of the concentrations are changing at the same time. It won't be easy to see which side was lacking. But hey, when in doubt, Q is always there for you. To get a better feel for this concept, let's have a look at the following problem. Let's say we have a Haber process going on in a closed container at 500 degrees Celsius. Now let's predict whether ammonia will be produced or used up if we add more nitrogen to the system. Even without the numerical values, we can analyze this problem just by looking at the reaction quotient when the changes are made. If we increase the concentration of nitrogen, we are increasing the value of the denominator, and with that, Q decreases and is now less than Kc. If Q is less than Kc, the reaction will proceed to the right. Therefore, more ammonia will be formed. To put it bluntly, since you put more reactants, the reaction will have to form more products in order to go back to equilibrium. Now, what if we remove some ammonia instead? Again, you can analyze it using Q, or you can just think that since you removed ammonia, there will now be a lack in the product side, and the reaction will proceed in order to make up for this. So, more product, and therefore more ammonia will be formed.
Now we move on to changing the volume or pressure for gaseous reactions. Here we can look at our old friend, the ideal gas law. Notice that you can get the partial pressure of a gas by isolating P, and then you get nRT over V, and N over V here, as you may have noticed, is just moles per unit volume, or concentration. Solids or liquids are only very slightly compressible, so they are not affected by changes in pressure. Gases do get affected, however. At constant temperature, N, R, and T are constants. If the volume of a gas increases, both its partial pressure and therefore its concentration decrease. The opposite is true for decreasing the volume too. Now let's consider a very simple gaseous reaction at equilibrium. We don't have to know what A or D is for now. Let's just imagine that this reaction is contained in a piston tank. Let's say you push down on the piston to increase the pressure in the system. Here's what happens. Looking at our equation for pressure, increasing the pressure will decrease the volume and thus increase the N over V, or concentration of the gas. Note that this applies to both the gases. Now let's look at the reaction quotient for this reaction. Before you move the piston, Q still equaled Kc. But after you increase the pressure, you increase the concentrations for both gases. So how do you predict how the reaction will proceed? If you look at the Q expression again, you will notice that the concentration of D increases more than A does because the concentration of D is squared. So the overall effect is that Q will be greater than Kc, and thus the reaction will proceed to the left. What if you pulled the piston, thus increasing the volume instead? Knowing that increasing the volume decreases the concentration, applying the same analysis to the reaction quotient, you will find that the reaction will proceed to the right. A simpler way of thinking about this is that if the volume increases, which means the pressure decreases, the reaction will go to the side with more moles of gas, and if the volume decreases, which means the pressure increases, the reaction will go to the side with less moles of gas. If both sides have the same number of moles of gas, the reaction quotient will not be affected by changes in pressure or volume.
Now we move on to the last way to disturb equilibrium, changing the temperature. Mathematically, things can get tricky very quickly if you analyze equilibrium disturbances when the temperature changes, because Kc itself changes with temperature. So we will do away with that for now. Thank goodness. In endo or exothermic reactions, it helps to think of heat as part of the chemical reaction. Now let's take a look at a generic exothermic reaction at equilibrium. Back when we were talking about changing concentrations, we mentioned that a reaction will proceed in the direction that either makes up for a lack or gets rid of an excess in order to bring itself back to equilibrium. We can apply that logic here, But now we put heat into the equation. If we increase the temperature of the exothermic reaction, we can say that more heat has been added to the system, so the reaction will use up this excess heat by proceeding to the right and forming more products. If we decrease the temperature, heat has been lessened, so that reaction will now make up for this by proceeding to the left and forming more reactants. The same train of thought can be used in analyzing disturbances due to temperature change in equilibrium of an endothermic reaction. The only difference is that heat is on the other side of the equation. Now some may ask, what about adding catalysts? Well, a catalyst affects the rate of the reaction, it definitely does, but it does not shift the equilibrium. It changes the forward and reverse rates equally, so the value of Kc overall does not change. In other words, a catalyst only makes a reaction go faster, but it can't knock the system out of equilibrium. To sum up what we've discussed, a system or reaction in equilibrium can be disturbed in three ways: by changing the concentration of the substances, changing the pressure or volume, or by even changing the temperature. There was also Le Chatelier's principle, which states that applying stress to a reaction will shift it in the direction that will reduce that stress. This principle, along with the concept of Q, can be used to predict the direction of the reaction once it's been disturbed. So, that pretty much wraps up our discussion. Thank you for listening, and have a nice day.